This is a production of Cornell University.
Okay, hello, and thank you all very much for coming, and very impressed to see so many of you. I have to admit, when it says Department of Classics, it also means not quite so many students. This is in the wonderful sciences area, so it's very nice to come here and talk about something else. So, in the course of one talk, trying to fit several different things, I was going to try and discuss, some of the evidence that we have for paleoclimates, that means ancient climate and change, and how this relates to human history and therefore human archaeology. Characterize what seems to be one of the major topics that everybody does at the present moment, which is to talk about crisis and disaster. We seem to be a society that likes crisis and disaster. Ideally, somebody else has it and we survive, but we like to spot them. And then to maybe suggest that there are other better ways of looking at the record of past climate and human history, sort of as a closing point. And one of the reasons for bringing in archaeology to the study of climate is most studies of climate and climate change today, and so far in our couple of decades, basically, there's been an academic subject. It involves doing something very expensive, like spending a lot of money to sail a ship out into the middle of the sea and you drill a deep core. Or you go to the Arctic or Antarctic and you spend millions of dollars drilling an ice core, and then you have to spend millions of more dollars studying it. Or you can do various forms of other records done on cave records like speleothems. But they're all sort of big science in a sense. It either costs a lot of money to get the samples, you need a lot of people to do it, the equipment that needs to be done, or you need to actually somehow convince Edwards in Minnesota that he's actually going to do it for you, and that's going to be a big deal. So are there other ways of doing it? And one of the ways of doing other type of climate science is dendrochronology. And I put this slide up, one, to show that it's just an amazing desert photograph. We're here in Jordan. We're just near Wadi Musa or Petra in southern Jordan. But the little green blob you can sort of see if you project upwards at an angle from Cornell University on the slide, that's a juniper tree. Trees in this part of the world don't look like you're used to. It could be described as a bush, but the difference is it's a 650-year-old bush. And it's one of the records that I've been working on in my lab for the last couple of years. And because it's growing in this area, and because it's still, being a nice tree, is growing 1 ring per year in this area, we have over a 600-year climate record also from this part of the world. And trees grow almost everywhere apart from the Antarctic and the Arctic. And of course, even then you can argue trees grow awfully close to some parts of these world. And if they don't grow there, some of the wood still drifts there. So by studying driftwood actually in the Arctic, you can find out a great deal about North Atlantic climate. So trees are very ordinary in some senses, but they are pervasive, and they give us a way of trying to study climate and environment that you cannot do from any other mechanism beyond a few hundred years ago. So my first little slide, just taken out of New Scientist. I'm not recommending the journal. I'm more just highlighting that this is the type of typical headline that one gets on ancient climate. You don't get told any facts or information. You get told fall of Roman Empire linked to wild shifts in climate. Now, if you read the rest of the text, you'll discover there's no evidence or quantification of what a wild shift in climate is. It's just basically alleged that there were wild shifts in climate. But this is the nature of the broadcast media. They want to have a disaster or a crisis, and then apparently it's worth taking an interest in. Now, it's transparently obvious if you look at deep time, and even this is very short time for geologists, so deep time for archaeologists, which means looking back several tens of thousands, so like last 100,000 years. It's very obvious if you look at any of the records that give you approximate temperatures for the Earth through that time, there have been major changes in climate. And this isn't a debate over whether or not fossil fuel extraction is good or bad for the Earth and all these things, so it's not a political debate. Simple fact that over time there have clearly been major changes in the Earth's climate. And in particular, if you look at during the last glacial phase, and I just got told this doesn't work, so I won't use it, you can spot that. I've just done a mistake there. You can spot that. We have these warm periods, the interstadials, and we have these cold periods, so-called Dangadoshka events, which are much colder. We can see that, and we can see a major shift at the end of this period to here, which is the shift from the last glacial period into what we call the Holocene, which until recent redefinitions over roughly here where the cursor now is, whether or not we have an Anthropocene that we're in now, that last sort of flattish period is the Holocene, which is remarkably different from everything that went before for many tens of thousands of years. Nonetheless, there seem to be some key significant changes in that, and you can see these remarkable warm interstitial interstadial events that occur. And these orange lines from this article, which must be a fact because it's published in Nature Communications, that's one of those high prestige type of journals that only real scientists get to publish in. So the allegation in this article is that if you plot the dates for various forms of important fossil industries made by early humans, and they are the little orange boxes you can see with the black lines, which are not really mentioned in the caption to the figure or the article, they're the error bars on the orange boxes. They allege that if you plot down from the orange boxes, they seem to roughly match up with the jumps in the blue lines, and therefore climate explains modern human evolution from in the Middle Stone Age. Even without binoculars, you'll spot that in fact the blue spikes and the orange lines don't really entirely correlate. They sort of match up a little bit. But more particularly, if you look at some of these error ranges, like take this one here, the error range covers, well, more than 10,000 years. So this isn't exactly a very specific correlation if we think about how long 10,000 years is. And this, I'd like to suggest, is one of the key points and problems in most paleoclimate and, generally speaking, human evolution goes with climate debates. Things involve what's been described as a suck-in and smear phenomenon, in which you sort of have one graph which you put in fairly general, often 10K type of increments along the x-axis. You plot something else on it, and at the resolution you're allowed in most of these journals or websites, which means it'll figure about this big, it starts to seem that the blobs and the spikes on the graph sort of correlate. You simply state there appears to be you don't use the word significant, because that would imply some sort of proper statistical test, but there seems to be a substantive relationship between the occurrences of these events and these spikes in the graphs. Therefore, climate explains history, or vice versa. Whereas in reality, I think we need to be a great deal more careful. In many cases, if you blow it up a little bit or look at the axis or ask about the error bars, it would be quite possible to redraw this diagram and suggest, in fact, the opposite correlation to the one in the paper. Now, if we look at that last little period, the end of the last glacial cycle and the beginning of the Holocene, there we can see the most dramatic shift and most dramatic rapid climate change event that we know of in the reasonable human past. And this is the event that occurs between the number 1 at the top, which is the Bolling Aleroid, which is the sort of last great interstadial period, it's the end of the last glacial period, plunged the last lot of cold temperatures, which is the Younger Dryas, and then we have this jump up, which has been sustained now for over 10,000 years of the Holocene. Does this seem to have a significant relationship with human history? And the answer, of course, is yes. And just plotted out a little more detail you can see there. If we consider the beginnings of what we call the Neolithic, now Neolithic means in terms of the language, neo-stone, neo-new lithic stone. It's the new Stone Age as it was christened, but the Neolithic has come to represent the first period in which we have semi-urban settlements of humans. So little villages are built, and I give you an example of what's called pre-pottery Neolithic A roundhouse down here, which didn't really work down here. And we get novel lithic industries that had never been seen before. And if we plot the radiocarbon dates once they've been screened and various forms of statistical manipulation have been done, for the Natufian, which is the last pre-Neolithic human phase, so this is still so-called hunter-gatherers, versus the dates for the PPNA, so pre-pottery Neolithic A, it's the very first recognized phase. How did that name come up? Don't ask me, but Dame Kathleen Kenyon came up with this name, and she's famous and has been for nearly a century, so it's the pre-pottery Neolithic A, as found at Jericho, and now many other sites across the Levant. And you plot a little box roughly around those dates. Everybody in the field agrees and has agreed for decades that the pre-pottery Neolithic seems to correspond almost entirely and exactly with the beginning of the Holocene. So in the Younger Dryas and even the period of the Bolling Aleroid, you had Natufian and nothing had changed. And right back to those Middle Stone Age industries of that second diagram I showed with the orange boxes, roughly the same. And all of a sudden, with the dramatic temperature change and other systems that changed with the Holocene, you get this entirely novel and new form of human civilization, which we call the Neolithic, which means settlements, permanent settlements in small village communities, entirely new forms of lithic technology, and rather critically, suddenly we're starting to, as a species, exploit other species. So we start farming. This is when the first grains and cereal crops start being both domesticated and harvested, and when animals like pigs and sheep and goats start to be domesticated, and we get herding and pastoral activity. So there, everybody since at least the 1960s would say Don't quite understand it exactly why X leads to Y, but there's clearly some form of correlation or correspondence between this climate change and human history and civilization. Now, if we look more widely around the whole of the globe, we'll spot that this phenomenon is something of a northern hemisphere one, because if we look at the sort of best records reconstructed for climate and a particular temperature from 3 different zones of the Earth, so the northern hemisphere, the equatorial region, and the southern hemisphere, and take this from this paper by Marcotte et al., got published a couple of years ago as a sort of community collective type of synthesis, you'll spot that the northern hemisphere is roughly doing what you just saw in the previous diagram. The equator is not really doing it at all, and the southern hemisphere, probably the best description is we need a lot more data to know what's going on in the southern hemisphere, but we do know that it seems to have the same change to the Holocene at about the same moment in time. But nonetheless, we have different patterns in different parts of the Earth, so that's something else to immediately bear in mind. We have a tendency to say everything's the same everywhere. In fact, it would seem that many of our climate systems are relatively local. Is the Holocene one big happy place where we've had more or less the same regime for the last 10,000 or so years? The answer is sort of, but with a few exceptions. One of the much discussed exceptions is the so-called 8.2 event. So that means 8,200 years BP. BP in this field usually being 1950, but sometimes 2000. This diagram I've used 2000. This is one of the great non-consistencies in the paleoclimate field. So at around 8,200 years ago, there's this dramatic cold event, which is recorded in a number of records from ice cores in Greenland. And the different colors represent, if you remember the figure that's 2 before, different ice cores. There was one called North Grip, one was called Grip, and one was called GISP. So Greenland Ice Sheet Project 2 equals GISP, and GRIP is Greenland Research Ice Project, and then there's the North one means north of the original GRIP, and there's Camp Century and several others. They all pick this up. There's this dramatic event around 8,200 years ago, and there's a slightly smaller one that happens about 1,000 years earlier, which is more debated. Other than that, actually, broadly speaking, the Holocene is remarkably benign. There's been a drying general desertification trend in quite a bit of the northern hemisphere mid-latitudes over the last 5,000 to 6,000 years, but it's been pretty gradual. A straight line is not a bad descriptor of what goes on from about 12,000 years ago to more or less the present day, minus the last couple of hundred years with the Industrial Revolution and effects that have happened since the 18th century. So what about this 8.2 event? It seems to be the single biggest thing that happened in the Holocene. How did that play out in terms of human history? Can it be found in multiple sources? And the answer is yes. So the 2 lines are representing it in different records. So you've got the ice cores up the top here. That's where it says North Grip. But down here we've got other records as well. So we're looking at various records of temperature. And this one here, particularly Sofalar Cave, is a speleothem from northwest Turkey. So a completely different type of record from a different part of the world. But it seems to pick up this 8.2 event. So as a result, because it's a big event, and it's back to my example of therefore you put things together without necessarily asking do they really go together, there have been a number of articles, with this perhaps being the most cited one, by Veninger et al., and you'll see there's a whole lot of et als, and a number of them are well-known and famous scholars in terms of either Neolithic or aspects of environment in the region. They write the title, Climate Forcing Due to the 8,200 Cali BP event observed at early Neolithic sites in the eastern Mediterranean. And this has been generalized to suggest that climate basically was a major force in the creation of the early Neolithic. They published this diagram, which I've now been looking at for nearly a decade and still have yet to figure out what they thought it showed. What it apparently shows, and you can think whether it means it's to you, is apparently the gray bar running down the screen is meant to somehow correlate with the histogram, probability histograms shown in the little curving lines in such a way as to suggest there's a meaningful relationship between the correspondence of the gray bar, which is the 8200 event, and the numbers and periods of occupation at various archaeological sites, which is represented by the probability distributions you're seeing running along the x-axis. Now, if it was only this diagram here, you might say, oh, look, there's nothing there. That's a bit significant, but then, of course, there's nothing here, and there's nothing here, and there's nothing over here. This one appears to have by far the biggest number of whatevers happening at the same time. So that doesn't look like one explains the other particularly, certainly not in terms of a disaster. If the article was headlined 8200 BP event creates or is positive for the Neolithic, you might think that one might work. This one, and there's a bit of a dip, but then this one's got another hump, And this one, well, you know, it's sort of a massively long low dip, but over thousands of years rather than just a couple of hundred. So although the article states quite clearly in its abstract that it has, apparently it says substantive evidence of a correlation between them, the actual material shown usually doesn't show it. And if we look at one of the most famous archaeological sites that covers this period that Ackermann's worked on in Syria, you plot the radiocarbon dates, you put a yellow bar showing where the 8200 BP event should be, and you'll notice there seems to be basically no break in occupation at all across this event, and this is where the tree rings are showing the 8200 BP event, and this is where the ice core is showing it. So at this major site, it doesn't appear that the climate event represented around 8200 in the various records is having any noticeable impact on humans. And although, of course, the university will probably come to a grinding halt tomorrow and snow or whatever, in macro terms, if you think about it, such events don't tend to have a totally defining event on our lifetimes either. In fact, the number of times you can probably think of a climate event that changed history in the last 100 years would be fairly thin on the ground, and those who've actually done some history would probably say, well, maybe, what about 1941 when Hitler invaded Russia? It sort of went wrong there, didn't it? Because it got really cold on him. And it was one of the coldest winters of the 20th century, so he was unlucky if you were going to be on his side, and the Russians were lucky if you were on their side, and obviously millions of people died, but you could say climate was significant there. But would anybody else like to volunteer something they can think of in the last few hundred years where climate was really determining? Okay, so dust bowl changes, which happen here, and we know that this has some correlation with the drought that happened in the Ukraine as well. And this corresponded with a period where Ataturk had real troubles in Turkey as well. So yes, there's a period in the 1920s where a number of historical events seem to have some climate relation. And of course, perhaps the most famous outcome of this is T.S. Eliot wrote a poem called The Wasteland, confronted by drought in southern England. The grass turned brown. So it was something of a disaster in southern England. But okay, an example, but there aren't lots of these events. They're pretty rare, actually, if you try and think of it. And many people probably would have said, well, there was Napoleon. He tried to conquer Russia as well, and it went wrong for him, because oddly enough, 1812 was one of the coldest winters of the entire of the 19th century. And again, you could say, bad judge, didn't have long-term records, didn't know what was going on, etc. But of course, there's no way of predicting that type of future. But actually, it's not that common to be able to think of such events, which makes it odd that we seem so keen always in newspaper articles to immediately link climate and history together. Now, if we relook at this 8200 event and consider some other studies, particularly this paper here by Pascal Floor, which was just published in Quarterly Science Reviews, they took a skeptical approach and a much more thorough approach. They actually went and found the radiocarbon dates for virtually every Neolithic site in the entire East Mediterranean. That's what you're looking at with all of these little bars being plotted here. And then they plot like the 8200 BP time period across here, and they observe, well, no apparent change as a result of that. They plotted on this map, which you can't really see, but you can just spot the little black dots. They plotted every archaeological site in the area known by time slice and observe no change in settlement pattern around about 8,200 to 8,000. It seems to be roughly the same. And so, on page 35 of this paper, in a very unscientific way, they write, in conclusion, there is absolutely no dated archaeological evidence for large-scale collapse or decline or migration at the time of two of the most severe and rapid climate changes of the Holocene. And this may seem obvious from what you've just looked at, but this has been deemed to be quite shocking in the field because basically they've suggested that 20 or 30 major scholarly papers which stated quite confidently that there was are absolute nonsense. And this is the nature of paleoclimate in which there are very few substantive claims have been made, in which carefully controlled evidence has been put together from both the human side and from the climate side, and then the question asks, how do they relate and why do they relate? Skip that one. Now, one of the few cases that almost has happened, and now out of, therefore, 12,000 years of Holocene, we're down to one of the few cases, already implies they're quite thin on the ground, is this one, which has been made famous by a man called Harvey Weiss, who's up on the top right, who's from Yale University. And starting in 1993 in a paper in Science, he suggested, with various collaborators, that something seemingly remarkable happened around about 4.2. For some reason, 0.2 is an important part of climate events in archaeology. So this is the so-called 4.2 event as it became. So around 2200 BC, the Akkadian Empire, which until that time had been one of the world's major superpowers, collapsed quite abruptly. And he observed that a number of other mid-latitude northern hemisphere civilizations also seemed to have major and radical changes in civilization around 2200 BC. And when you plot a whole series of paleoclimate come paleoenvironmental type of markers, and you can sort of roughly read these are lake cores, Golishar is another lake, Lake Van, down here Dead Sea, and if you keep going all the way down, we come to things like the Mount Logan record. You can see where the grey bar is running through. A number of these records do seem to show some form of spike or change or significant oscillation and pattern around about 4.2 to 4,000 years ago. And he argues the event lasts about 200 to 300 years, so from about 4.2 to about 3.9 thousand years ago, or 2200 BC to about 1900 BC. Correlates with the time of what's called the first intermediate period in Egypt, correlates with what's often been recorded as a dark age in East Mediterranean and Near Eastern prehistory, correlates with some changes that happen in the Indus Valley, so it's quite widespread. And to his credit, Harvey, unlike everybody else, actually thought it might be quite a good idea to try and figure out, well, can we really date this? Rather than just allege, can we actually date it? And actually, let's say a couple of other events. So, bristlecone pine record in the American Southwest dates this event not just accurately, but precisely to the year. So we can actually see that trees start to be too far up the mountain. So bristlecone pine is one of these long-lived species that lives right at the upper timberline. So when it gets dramatically colder, they're actually too far up the mountain. And unlike in Tolkien, trees can't walk, of course, like Ents. So if you're suddenly, the upper tree line is now 500 feet too far up for the much colder conditions, the trees actually die. So we have remnant populations which tell you when a really significant downward climate change happens. Similarly, as has been happening recently, younger bristlecone pines are progressively heading up the mountain because it's getting warmer and warmer, and there's a longer growing season. So we can date this event in terms of years, in terms of the bristlecone pine record, and you can see this dramatic change in which they drop off the record just here. And there's another Indian record which shows the same dramatic spike around 2200. So here comes the archaeological bit. So normally with many of these paleoenvironmental records, it's difficult to actually get a really precise date or any tie to human history. But at a tell site, so that means a site at which people have repeatedly lived in the same place and built up floor level after floor level. So you can actually stand and look at basic little mound and say, that's all human debris of occupation through time that you can see. Like Tel Leyland, the name gives it away. You can then apply other types of scientific evidence, particular radiocarbon dating, and in particular then applying a technique called Bayesian chronological modeling to the radiocarbon dates, in which you say you radiocarbon date something, and that gives you a probability of X. But if I know that this thing here occurs before the computer screen, which occurs before the table, which occurs before the floor, I can then say, not only do I have the individual bits of probability, but I know in advance the order in which those must be, and I may even have some information about the spacing or the time involved. And Bayesian chronological modeling, as with any Bayesian approach, allows you to combine together all of those prior pieces of information along with the newly observed piece of probability or sets of probabilities to then constrain the answer that comes out the far end. So what you're looking at is a representation of such a model in which oldest time is up the top, most recent time is down the bottom, and each of these little boxes that you can see sort of capturing things, these are elements which are archaeologically attested as being before or after the other ones. So there's an ordered sequence from oldest at the top to the most recent at the bottom. You then radiocarbon date, and you get radiocarbon dates for lots of elements within this, but they're constrained by that known seriation. The end result is, rather than getting radiocarbon dates as typically for a random object, like if we dated this pointer if it was made out of something that's sort of been growing organically versus petrochemical, we'd get back a number and it'd be like plus or minus 50, and probably by the time we'd turned it into a calendar age through a thing called the calibration curve, it'd be like a 150-year range. But instead, we can actually date something like the end of occupation at Tel Leyland, and that's the ones on the right in the screen. Using this technique, we can start to actually be describing it as most likely occurring within less than a 20-year range. And this one down here, I take out a few little outliers out of this one, most definitely within that. So we can start to say, well, Weiss was onto something, because even at 95.4% probability, the end of this whole occupation. The site's been busily occupied and then suddenly is completely abandoned. And it's not just the site, it's every site in several square kilometers around it. 95% probability, 2240 to 2196. So there's like a 40-year total range with a very high degree of confidence. So now we can say, well, perhaps he's onto something, because actually the most important site, and this was the capital of this empire, it wasn't just some random little place, it's actually coming to a complete end, and as are all the sites around it, and in fact, as are all the sites within a huge survey area that they did in northern Syria, obviously before the war. So now, when the bristlecone pines are dying at literally almost the same time, maybe he's onto something. Now, this event, Harvey describes confidently, was caused by a deflection or weakening of the Mediterranean westerlies, and the Indian monsoon generated synchronous megadrought across the Mediterranean, West Asia, the Indus, and northeast Africa. Dry farming, agriculture domains, and their productivity were reduced severely, forcing adaptive societal collapses and regional abandonments, habitat tracking, and nomadization. Fairly sweeping. He's falling victim to the need to have a sort of overarching, complete, comprehensive explanation. And this is where I then part company with Harvey, because he hasn't asked the question, does the same problem that he's observing, because where he is, which is his site, which is up here, it says Leyland, and these purpley bluey colors are representing rainfall levels in the modern day, which we're going to have to assume are roughly what they were in the past, because we don't have meteorological evidence that that's far old. His site is just about at the transition where you start to only have about 400 to a bit more millimeters of rain typically a year. Now, you need about 300 millimeters rain reliably to grow wheat. Barley you can get away with between there and about 200, 250. So Tel Leyland is a sort of marginal but okay cereal growing location in good years, but it only has to become a little more dry and it's moved into distinctly marginal. So he's in a susceptible situation. It would be like living in Ithaca and relying on something that was wasn't frost tolerant, meaning that well, as soon as it freezes, you're in trouble. Well, you're going to guarantee it's going to be a disaster. And as you head progressively further south, you'd get to a point where the economic balance would be such that sometimes, some years it'd be okay and others it wouldn't, and you have to try and decide. So although he's correct undoubtedly that he has a major change event here, and the dates is really good, maybe it doesn't apply everywhere in the world. It depends on what you're susceptible to. Now, various books have been written, and I just give a couple examples here. People like this, and particularly this German one here, that's just what? A climatic breakdown as cause for the collapse of the old world. This seems to sell, of course. But what about if we look elsewhere in the old world, and particularly if we look in Asia? What's going on, for example, if we look at some of the speleothems that have been produced from China, where some of the world's most high-resolution speleothems now exist from? There, we seem to see something similar in the sense that there is an event occurring. So if we look around this same region around 4,200 just after, you'll see there's a sharp change in gradient in some of these records. So something does appear to be occurring in some of these records. And we can go and look somewhere very sensitive there as well, because if we go and look on the Tibetan Plateau, this is one of the most temperature-sensitive regions on Earth. So good place to have a look to see what's going on. And in particular, looking at two regions, which I'm just defining here as northern and southern Tibetan Plateau. There, if we do the same thing and look at radiocarbon dates for various forms of human activity, is there a pattern? And there seems to be a striking one. So if we look at the sites that have a crop called millet, which was the crop that was used by nearly all human civilizations in this area from at least about 5,000 or so years ago, we notice that all of them have millets, that's the blue, and then suddenly, just after this 2,200 period, starts to drop out and change, and from that point on, all of the sites have the red ones, which is either barley or wheat. So at this very same period, there's a dramatic change in the basic subsistence crop in an area that's both has a long and old civilization and has a large population by this period and continues to have a very large population and rapidly becomes a state and empire civilization. If we model the temperatures required for barley and millet, again, obviously you have to base this on contemporary examples, so there's always the possibility of land races that are much different in the past. We can see that the temperature was very suitable for millet until around 4,000. And then the probabilities, that's on the left-hand side, of millet being in the right temperature niche starts to fall away quite dramatically, whereas wheat and barley are right in it. So a temperature-linked change does seem to be occurring here. So again, it would seem that Harvey Weiss was correct that some significant climate change affects the Earth at this time. But the difference is, I'll skip that one, the difference is, sorry, that's the one I actually do want. The difference is what's causing it and what's its impact. So the cause is debatable. Weiss said they did not know what the cause was, even wondered about volcanic activity. Mayuski et al. Said that it's more difficult to attribute the less widely distributed rapid climate change at 4200 to 38 to a specific focusing mechanism. The former, he says, coincides with a maximum in beryllium 10, but there is little change in delta radio 14C, which is changing levels of 46 at the time, to suggest a solar association, so suggest that there wasn't. Now there they seem to be wrong, because if we actually plot solar irradiance records, there seems to be a significant change that happens around about 2200, 2000, which we've had a long period of one direction of progressive change, and then a rapid change in an inflection in another way. So it would seem that maybe a change in solar irradiance is rather key here. But perhaps rather more relevant is that this change, which happens, is one that leads to a fundamental shift in food regime in a part of the world that has, well, more people than anywhere else, both then and today. And rather than being a crisis, as it was in the Akkadian world, actually this was very much the beginnings of what became Chinese state and empire. So the very same phenomenon has an extremely negative effect in one part of the world, which is susceptible to one particular thing, which is declining rainfall that's happened in northern Syria. But in another part of the world, it actually led to a system change which actually benefited humans, assuming we say more people is a good thing, so we don't have to have the argument about whether that's a good thing or not. But it was effectively a productivity increase in terms of human civilization. So different outcomes from the same event. So immediate conclusions or observations. Studies of the collapse of societies usually find no single climatic prime mover, rather a complex set of different issues in many cases. And even where we do have a climate driver, like maybe the sun in this case, we see forms of human resilience versus collapse and other things are going to occur in many cases, and there's no single one cause, one answer. So back to this question of the decline of the Roman Empire and what caused it. There we have the same phenomenon in many ways of what things do we link together. So a variety of papers in the last few years have tried to find one single driver. So this paper, which was by Neil Peterson et al., based on tree rings, looked at the tree rings and said, oh look, there seems to be evidence of increased rainfall happening around about this time, which is around about sort of 13th century. And this is about the time that Genghis Khan had a lot more horses and seems to have been able to invade the rest of Eurasia and create the Mongol Empire. And therefore, rather extraordinarily and fairly simplistically, Peterson et al. Simply said, well, that's the explanation. Because there was this period of sustained better climate, more rainfall, there was more grass, therefore there were more horses, and therefore Genghis Khan invaded the world. Now, the first two parts of that are not implausible. Because there was this period of sustained more rainfall, there probably was more grass, and there probably were more horses. But why that means Genghis Khan invades the rest of Eurasia, of course, is unclear, particularly given that they too would have had more grass and more horses, and it doesn't actually particularly make sense. But nonetheless, again, it was published in a leading scientific journal, so it must be correct. The more recent one, published last year by Ulf Bunkton, who usually is a careful and good scholar, tree ring specialist, along with many others, they have found a new period, which they've christened the Late Antique Little Ice Age, as distinct from the Little Ice Age. And this happens in the period at the end of the Roman Empire and the beginning of the Byzantine. And they have plots like this in which you see various forms of climate indices going up and down madly, and it looks like sort of, somebody who's drunk trying to draw a straight line or whatever. And then they plot a whole variety of apparent social events which happened within this period. And they're a bit thin on detail, but if you try and scribble down the bottom, it says 540 there and 700 over there. So that's almost 200 years, 160 years. And they put all of these little black things progressively through that. And somehow this cool period, which they're calling this Late Antique Little Ice Age, semi-explains all of these, even though they're occurring over the best part of 2 centuries. which seems problematic again to begin with, because we know enough about human history from our own sort of experience and the period of the last few centuries that we think we know really well, to know that rarely has anything happened continuously and in one direction for a couple of centuries in a row. It just doesn't tend to work that way. I mean, we're still much less than a century since the Second World War, and yet we would say we're in a completely different world from the one that happened then. We're a great deal less than half a century away from the Vietnam War, and yet we'd say we're in a very different world from that one. So this concept that in the ancient world that you might have actually had 160 years of seemingly coherent decision-making, other things, seems unlikely. And we have another very loose relationship between climate and the human record. And then critically, at the very end of the paper, the authors write, although any hypothesis of a causal nexus between the volcanic-induced 6th century unprecedented thermal shock and subsequent plague outbreaks, rising and falling empires, human migrations, and political upheaval requires caution. And they then suggest you've got to be a bit more careful. But they've just spent the entire 4 pages previously showing no caution whatsoever and a very positivist A equals B, rather than maybe A plus B, C, D, and E somehow might partly explain, F or something like that. Now, in an earlier study that Bunkton et al. Had published, which was the one that went with that while shifts caused the fall of Roman climate, they'd published a diagram like the one on the bottom left here, in which they'd argued that this dramatic change in precipitation up and apparent change in temperature down here, that probably had something to do with the fall of the Roman Empire. And arguably, and point maybe to sort of change to my other point or topic, would be to say, rather than doing that, wouldn't it be more interesting to perhaps observe in a similar diagram that the period of the Roman Empire is noticeable for actually being very flat. Nothing much is happening in the climate record. And you can see the same in the box over here. So rather than just looking for a sort of blip in one of these graphs and saying that must be something dramatic, maybe we should actually look for the periods of time when there weren't any great blips, and these may have been very positive for human civilization. The Roman Empire is instructive in this regard. If we look at the record of major volcanism that we have from several different sources, one of the notable things is that the period of the main Roman Empire is very non-active in terms of major global volcanism. Major volcanisms, that's very big eruptions with large volcanic explosivity indexes, so things like Mount Tamboras and bigger. These are one of the short-term major climate drivers. Everybody accepts that. But if we look at the record as known, for example, in the period from about the 1st century BC through to the 4th century AD, there basically aren't any. And even if we look more widely, the whole of the sort of classical period is pretty low scale in terms of major volcanic activity, and in great contrast to many other periods. And, for example, this is the so-called late Antique Little Ice Age, this period over here, where there are a number of big apparent volcanic eruptions. So rather than saying we should focus on the little spike over on the far right-hand side, maybe the more interesting thing is everything that's regarded as successful about the Roman Empire lies in this period when it's basically quiet. And apart from quiet, we get some periods where maybe we can say that things are especially favorable. So one, for instance, is what happens in periods after cooling episodes. We know about one of these quite well. It's called the Maunder Minimum because it was actually observed. We actually have records saying how many sunspots there were during this period, and the sun basically has almost no sunspots for a period of several decades, which means that the sun was relatively non-active, which means it was generally speaking cooler on Earth. And that's the one I've highlighted with the little bar. And if we look at reconstructions of rainfall across Europe and the Mediterranean, we'll observe that in the 50 years following the Maunder Minimum, which is the one at the bottom right, it's by far the most consistently moist period in the record of 1,000 years that we have, the last 1,000 years. So this is a period which would have been consistently good for agriculture and human populations across most of Europe and the Mediterranean and Near East. Now, right at the far north, where it starts to be colder, reverse applies. This would not have been the best time to be living in northern Sweden, for example. It would have actually been cold and very snowy and so on, and not quite so good. But for the heartland of so-called European civilization that people would be looking at to say what's going on in the world, particularly in this period around the 17th, 18th century, it was a very good time. It's, of course, noticeably also a period in which we have major expansion into the colonial enterprises into much of the rest of the Northern Hemisphere world. Now, the sun is probably the driver behind these sorts of events, and if we look at the record of solar activity, which is the one with the little yellow arrow, we can see various periods where we have these dramatic solar episodes like the Maunder Minimum. And if we look into the past, some of these seem to match up with history. So the one that happens around the 8th century BC seems to be followed by the so-called Renaissance of Greek civilization, it's often termed. This is when Greek colonies appear all over the Mediterranean, so that's all of the little red dots that you can see over here. And this is when the first figurative vase painting appears in the Western tradition, but it's also a period when civilization in the steppes and Scythian region takes off, and it's also the beginning of a major state period in China that we know of in East Asia. So there's a link, it would seem, between certain of these changes in solar activity leading to these long sustained periods of increased moisture and relatively consistent temperature. And I'm trying to show that. So this is the period before the Maunder Minimum, and you'll spot that most of the little black graphs go upwards, which means moister and more favorable afterwards. And we have historical records that seem to attest to this occurring. So, for example, in the 9th century BC, Assyrians based in northern Iraq started a relentless process of expansion that within 2 centuries would see them controlling most of the ancient Near East. And they were doing this in that very period when the Greeks were starting their vase painting and so on. So right across mid-latitudes of the Northern Hemisphere, this period following the 9th century solar minimum was very positive in terms of numbers of people and development. It's necessarily positive that they started a period of remorseless expansion. So most work has so far focused on climate as a threat and rather than a context, and in some senses the real challenge, I think, going forward for archaeology and history and climatology is to actually start to get away from that type of reductionist paradigm where you just look for a disaster, but rather to say, how does this relationship work, and particularly, how might it explain history? And here we can bring in politics. So Donald Rumsfeld, the other Donald, came up with this wonderful and famous statement, which has been much cited by many people, about known unknowns and known knowns and so on. But it's a relevant way for how people do think. And in particular, for most human civilizations, and particularly in large areas of the world, the real danger for their subsistence regime comes from things like drought. So they've evolved a civilization in which they know that they have unpredictable weather, but it fits within a sort of range. And the typical example is most peasant farmers and most ethnographic studies have been done almost everywhere, try and have one complete cycle of seed available beyond the one they're using this year to allow for a bad year. So they hope to be able to ride out one bad year to get the next one. And this is why when you then have multiple years that are completely disastrous, all of these adaptive regimes break down, and then you have a humanitarian crisis. So that's the unknown unknown, as opposed to the known unknowns, which is there will be a drought sometimes, but how often you don't know. And if you're Joseph and you happen to, get divine intervention, to put your store in for 7 years and be ready, but everybody else has to take a punt and say, oh, well, maybe, probably most of my lifetime, 1 year will be fine. Now, occasionally we know that the world has not been friendly. And we know, for example, from the work of Ed Cook et al., that in the early part of the most recent millennium, so we'll say second millennium AD, there were several periods where there were long sustained droughts, which have now been christened mega droughts in the American Southwest. And these would have been disastrous for people living there. And this is basically the end of the Anastasia and other groups. And we can have some contemporary records that occur at such times from Greco-Roman literature because we have texts. And we don't have to read the whole of this one, but it reads like a very depressing CNN report if you had visited a drought or disaster zone. This is an account of what it's like to live through a famine in Odessa. So, what is a climate subsistence crisis in the pre-modern world, and how common are they? And if we look beyond that, how important are these things to human history? And what do we actually know? Well, of course, one of the most surprising things to a modern audience, everybody with their smartphone and expecting to be told everything at once, is we're incredibly ignorant about the past climate history of the one planet that we live on. which you would think was important because it's the only place we've got to go at the present moment. This diagram shows the depth of time we have climate records just from parts of Europe and the Mediterranean, which would count as one of the best known parts of the planet. And everything that's blue is 1800 and more recent, and only if it's in the yellow-orangey colors do we have any form of climate record from before 1800, which isn't really very long ago if you think about it. Who believes they know? What's the oldest continuous temperature record that we have on Earth? Anybody know when that starts? The answer is 1659, Central England, as a result of one bizarrely inspired reverend who started doing this with a thermometer. But mid-17th century is the oldest continuous record we have from anywhere on Earth. So when you think about all of these arguments about whether temperatures are going up or down or otherwise, everything that we know relies on then coming up with some sort of proxy record by calibrating modern instrumental records against tree rings, against speleothems, against ocean salt, against whatever, all of which have many issues and problems, and they're all, effectively, an algorithm is written to try and best correlate, X to come up with a fudge factor that you project back. So remarkably, we know very little about a great deal of the planet in terms of climate. This became very evident in the first Gulf War when it was discovered, of course, by the US military that we didn't have any climate records for Iraq that went back more than 50 years, which seemed a very bad basis for guessing what was going to be faced by troops in the field. And so suddenly more money went into trying to do this. But we do know, by even studying the last 50 years, and for many parts of the planet we literally only have about 50 years of climate data, that it's entirely wrong to believe that there's any consistent pattern. And in fact, as this map's trying to show, a relatively small area of the Earth can have very divergent climate patterns at the same time. So the blue, of course, represents reasonable amount of moisture, and the yellowy-brown colors are representing progressive stages of drought. And what you'll spot is that at the very same time that parts of, e.g., northern Anatolia, so northern Turkey over here, are doing okay, well, just over here in Greece, they're apparently in desperate drought, and they're not actually very far away. Most of Italy's having a bad time, but then parts of southern Italy are actually going well. Most of France is fine, but a lot of Iberia is having a really tough time on average. So a lot of regionalism, which means that when you're writing about history and climate, you can't just pick one graph out of some convenient popular science book which says, oh, this is the record from Greenland ice caps that says this, averaged over 100 or 500-year intervals. Actually, it's going to be quite a local record that you need to study if you're going to write any meaningful human history. Now, ways of trying to get at that are from things like speleothems, so cave records can exist from a large number of locations on Earth, and increasingly people are building these up. Tree rings, as they began at the beginning, are one of the key sources, and they exist, and this diagram is trying to show you up the top all of the different sites for which tree ring records exist, so in this part of the world, so a lot of parts of the world tree ring records, but as the diagram at the bottom right showing, only a few of these actually go back more than a few hundred to 1,000 years. There are very few continuous records that go back more than 1,000 years. So that needs development. What do these sort of records look like? Well, here's a very instant example. These are Pinus brutia trees from Cyprus. This is a project my lab worked on a couple of years ago. So we built a 250-year annual precipitation record here from a low elevation site. So this is a site where people are actually living close by. One of the problems with many of these climate records is they're brilliantly constructed, but they come from some location that's about as far away from where humans live as possible because it's up the top of some mountain, or it's in the Arctic, or it's wherever. So these are actually coming from trees near people. What you do is you compare your tree ring record against the known instrumental record for the period that exists, which is often a very short period of time, at most usually a century. You calibrate them together, and then you use that calibrated fudge factor then to extrapolate backwards. And what did we observe? We observed that in the 250 years we had, Cyprus is meant to be this really dry place. The government was quite convinced it was always having a drought and was planning on that basis. And we discovered that the last 250 years, there actually really only been 8 serious droughts. I mean, that's a lot more than some parts of the world, but there's wrong to believe that, of course, you have a continuous drought. Rather, every 40 to 60 years, there was a serious drought, which is very different from saying there's always a drought. Those are the years in which you get such droughts. And they correspond with records we have from historical and modern archives. can we look at history to give us much information? Well, there are lots of historical records, and some of them even mention climate and problems, but it's very patchy, meaning you get one particular bishop, which is this column that you can spot here, who likes to write a lot to his friends to complain about how cold it is and how he has bad rheumatism and things. And then you get other periods of time, like over here, where you can see a whole 50-year period where basically nobody that we've discovered wrote anything about climate. It doesn't mean there wasn't climate, we just don't happen to have a written record that belongs with that. So it's very difficult to use history beyond a few hundred years ago. Mapping together lots and lots of tree rings is probably one of the best ways of doing it, and Cook et al. 2015, that the Cornell lab here was part of, along with about 50-odd other laboratories, we attempted to put together nearly 2,000 years of record for what we call the Old World, which is the region you can see over on the right-hand side of the screen. But even then, it's only 2,000 years, and of course, if you're a climate skeptic, you're going to say, surely we need to know it over 5,000 years, or however long before I'm going to believe things. So we need to build more of these long-term high-resolution records, and not just from one place on Earth. I'll skip that one. And then the most critical thing of all is actually tightening up the climate records. Most of them do not have the chronological resolution either of the archaeology or of things like the tree rings. So I pick an example here, which Kanievsky et al. Published in PLOS One only a couple of years ago. The article had a title that was explaining this data explained the end of the late Bronze Age in the East Mediterranean. And they had done pollen and other forms of record, and they showed, as in my little box, all of these black lines are all plunging down, supposedly. And they all did this around 1200 to 1000 BC. And this would explain the end of what's called the late Bronze Age in the region. And I saw this, and I thought, well, this is quite impressive, isn't it? They've done something interesting here. And you always immediately think, I wish I'd done something like that. That looks good. And then you finally get the data, and you start thinking about it. Then you realize what's wrong. And the what's wrong was in the table at the top. This entire time scale that they're putting all of these lines on was on the basis of 3 radiocarbon dates. And they hadn't even done any particularly clever modeling with them. In reality, if you plot their 3 radiocarbon dates against depth for their core, and you calculate the probability of dating around and between those 3 radiocarbon dates, you get a plot that looks like this that I published with a colleague last year. And for the period of interest, actually they have a dating resolution that is in the hundreds, if not basically 1,000 years. So in other words, it's an utterly bogus claim. They haven't resolved what happened around 1200 to 1000 BC. They've resolved what happened between about 2000 BC and about 500 BC at best. And of course, there's probably was a drought at some point in that period, but it doesn't in any sense tie between this end of Old World civilization, as they're trying to claim at the end of the Late Bronze Age, and a particular event. This type of thing occurs all the time. Another set of records which was published all claiming to talk about the same thing are these ones, which come from various caves and ice cores and other things. And they all claim to be explaining this event again at the end of the Late Bronze Age where the grey bar is. But you'll notice, as plotted according to their best timescales available, I have had to, with my little arrows that I'm indicating here, you have to basically, the phrase in paleoclimate is tune. Tuning means moving things to make them work for you, as opposed to there's any real basis for doing it. You have to tune all these records by, in some cases, hundreds of years to make them correlate with each other, which defeats the whole point of having got high-resolution records. High-resolution records are meant to define the timescale, and then you can follow up, not that you move everything around so as to find an event with your high-resolution records. So to end, we have our farmers, and we have lots of studies, and I just put a couple of random books up here, who have studied how people subsist in pre-modern times before you rush down to the local Wegmans and just buy things and come back. So when you have to grow things and know how it works, and how most of these societies can cope with crises for, at most, usually 2 consecutive years. And we have various records of how often types of crops fail in particular areas based on crop records either for the last 100 or so years and various observations. And people like Peter Garnsey have written books discussing some of these things and the frequency of crop failure. We more particularly can look at the climate records for places like maybe the northern Levant or Cyprus, and we can see for given locations over the period we have instrumental data that areas that grow wheat and barley, particularly in central Cyprus, this is northern Syria here in central Cyprus, often have situations where most of the time the crop would be fine, but the grey bar and the red box represent when the crop wouldn't be fine, but then every few years they plunge into this not fine zone. But what you'll observe is not once do they do it 2 years in a row. So in other words, the well-prepared farmer would have had a bad year or even a failed harvest, but they would still would have had their seed ready to go the next year, and they would have had a tough year. They would have undoubtedly had to kill some animals or sell something, but they would have had stuff to sow, and it would have grown the next year, and they would have survived. And we describe this as being resilient. So it's quite rare to see 2 bad years in a row, and certainly 3, which would really be a wipeout situation. Now we can use dendrochronology to try and explore this on a slightly longer term basis. How often do we have such a disaster? Now if we look at southwest and north Anatolia, so the Aegean region, we have nearly 1,000 years of tree ring records, and we can plot the precipitation by the year, and we can model that pretty accurately. And as you can see from the diagram, it goes up and down madly. And the grays are showing the light gray is the 1 standard deviation range, the dark gray is the 2 standard deviation range. And if we say that something that's bad, like no rain, outside of the 2 standard deviation range, that probably was really pretty unfortunate if you were living there at the time. And then I've plotted, with my little crosses and stars, where you get 2 consecutive years less than 1 standard deviation, stars are less than 2 standard deviation. If you look across the bottom, what you spot is there are no situations where the 2 stars are right next to each other. There's one time here where they're not far apart, but usually they're decades, if not century, apart. We can look at the more recent period, and we see the same thing. The stars are very rarely closely together. There is a really interesting one just there, and otherwise not. And if we turn that into a table, and we look where we have data, we discover that in the past, circa 900 years, only twice have there been 2 consecutive disaster years right across most of Anatolia. So Peter Gowans, in his book, and quoting Amartya Sen, who's a famous economist and development studies person working in India, commented on the fact that food problems in the third world or sort of pre-modern world are commonplace, meaning they happen almost all the time. And that's back to the graphs, it's going like this. Every few years there's a challenge. Genuine food crises, which means people die, lots of them, are very rare. Now, he made that on the observation of what he had available in 1983, which was not that much really in paleoclimate terms, so it was quite prescient. Here we are with 2017-ish data, meaning this graph and diagrams should be published this year. And we can observe that over a 900-year high-resolution record, twice in 900 years do we get that. Now, one of them, the one down the bottom here, is the 1927-28 one. Well, that's modern times. Ataturk had trucks and telephones and airplanes, and you could actually fly places. So you could move things around. There were big ships. It nearly brought his regime down, and of course it was a totalitarian control type regime, so he had the ability to enforce things. It still was the single biggest crisis he faced, but it was a modern situation. You could telegraph people and tell them to send stuff even if they were 500 miles away. So the only one that really happened was this one at the very beginning of the 17th century. It's also the period that's known as the Shillelagh Rebellion, and this was the time that the Ottoman Empire, which then was the world's greatest superpower, almost collapsed. It had a huge rebellion. The empire was more or less on the ropes and barely got through. So in 900 years, you could argue that this was the one time there was an historically forcing climate event which had a major impact on Western, Central Asian, and European civilization, because the Ottomans were the dominant player, and it led to major changes in the Ottoman Empire. They changed the whole tax regime, a number of things. So yes, we had Napoleon, and you had a bad time, and yes, we had Hitler and the snow, but maybe you could argue that the one utterly fundamental one is this one. And my point, therefore, being disasters are remarkably rare and occurring on a sort of, once or twice a millennium type time scale, or just occasionally like the beginning of the Holocene. What we should really be looking at are the other periods in which we have stable conditions or benign conditions which allow for humans and their adaptive regimes to succeed and to multiply in a big way. And they may often be ones that apply in one part of the Earth, like in Tibetan China around 4200 BP, and not in other places, like northern Syria, where the same conditions led to drought and other problems. I will stop at that point. Thank you.
This has been a production of Cornell University, on the web at cornell.edu.